Okay, so today we have Eigil Rischel. He's at the University of Strathclyde, and we're lucky to have him visiting Topos for a couple months. And today he's going to tell us about lenses, optics, and all that. So thanks.
Yes. Thanks, Evan. Yes. So yeah, this is going to be pretty informal. I'm just going to give a kind of survey of these various different constructions that are known by, various types of like cut glass, and the kinds of things that people use these things to think about. And if I have time, I'm not sure I will, at the end I'll talk about some work in progress on a kind of generalization of this that we've been working on at Strathclyde. Right, so maybe I'll just start by telling everybody what I mean by a lens. So lenses. So many years ago, on some time scale, like not centuries, but probably more than 10 years at this point, people doing like functional programming came up with this idea of a lens. So a lens, A to B, and here you should just for now let's just say A, B are sets, is a get function from A to B, and a put function from A times B to A. So the kind of interpretation of this is that this is telling you how to kind of access a field containing elements of B inside elements of A. So for example, if there's a lens from like x times y to x, which we could call.
Would you be going to differentiate there?
Oh, the arrows. That is a good idea. Maybe I'll put else on these. So there's a lens from x times y to x, where the get of like x comma y is x. So how do I read an x out of this thing? I just take the first thing, and to put x, y, x prime is x prime y. How do I set the x field to x prime? I just replace it with x prime. Okay, so this is a kind of approach to data structures, to a relation between two types of data structures that tells you how to locate one inside the other. And so there's tons of neat things about these. One of the neat things about these is that you can compose them. So if I have two lenses, let's call this one let's call this one phi from A to B and psi from B to C. Then how do I compose them? Well, get of phi compose, I should use phi compose psi, is just going to be get phi compose get psi. So if I want to read a C out of an A, and I know how to read a C out of a B and a B out of an A, I just do those two things in order. And so put now let's think about how to write this. So put phi compose psi of, so the inputs now have to be an A and a C. So if I want to set the C value in A, how do I do that? Well, I'm obviously going to have to use put phi to set something in A, and now I need something of type B, and the way I'm going to get that is that I'm going to use put psi to set something to C, and the thing I'm going to set to see is the C field inside the B part of A. So I'm going to use get phi to get that. Okay, so this is a little bit and match parentheses. This is a little bit like this formula looks a little bit complicated. Part of later we'll see kind of a more natural way of thinking about this. But yeah, so this is kind of how to compose lenses. And so people came up with this in kind of computer science, and then they invented a whole bunch of different things to do with these things. And then, in a completely different part of the world, somebody was thinking about game theory. So, there's this, in 2016, well, not a completely different part of the world. I mean, this is Jules Hedges in 2016. So he was thinking about how to use category theory to describe game theory in the sense of economics. So you want to talk about how different kind of, you want to decompose a game into kind of the different agents and how they interact with each other. So he came up with this definition. So an open game consists, this is like a morphism in a category. It goes from xs to yr, and again, all of these things are supposed to be sets. X, y, r, s are sets. Consists of the following data. So we have a strategy set. Which is called sigma. A play function. Which, let me just write it as P from sigma times x to y. And this is slightly weird, a coplay function, I'm going to call it C, from sigma times x times r to s. Okay, and so this is actually not the definition that's in this paper. This is that later one, which is the one that Jules prefers now. So I'm going to use this one also because it's simpler. So an equilibrium relation, or an equilibrium predicate, which is like epsilon, and this is a subset of like sigma times x times, and then let me write this like this, the set of functions from y to r. Okay, so let me try to unpack this definition a little bit. So you have it like, you can think of an open game as kind of describing, an agent that kind of is interacting with the world through this interface. So you have a set of strategies, sigma, which are kind of the set of choices you can make, or the set of kind of ways that you can choose to play the game. So in the simplest cases, this will just be the set of functions from x to y. Then what happens is you see an x, then you kind of choose, you somehow output a y, and maybe you can choose to output any y you want, but maybe there's some restrictions on that. And that's, the play function kind of tells you for each strategy which choice are you making. Then there's this coplay functions, which tells you, then some other stuff happens in the future. Eventually you get one of these r's back. R might be the set of real numbers if it's like your reward. And then somehow your strategy also passes some information back to the people who are behind you in time, which is this S. That's the information you're passing backwards. that's being modeled by this coplay function. And then the equilibrium predicate tells you for every x and for every function from y to r, so for every, this is sometimes called a utility function, this is the function that tells you what you get depending on your choice. There's some subset of the sigmas that are in equilibrium, which is supposed to mean good. They're like optimal. They're choices that you want to make one of those choices and not another choice. Yeah. So this, as I said, this is not exactly the definition in the original paper, but this is simpler and good enough for game theory. Yeah. So this is the definition of open game. I have to tell you how to compose open games if I want to convince you that this is a category. And the formula for composing open games is like extremely complicated. And so therefore I'm not going to write it down, because the observation that Jules eventually came up with was that this is essentially lenses. Which is, so, you have for each sigma a function from x to y, and for each sigma a function from x times r to s. And this is, this is almost like this, except that, the things that are going backwards, like the b here is not b anymore, or y anymore, it's r, and the a here is not x, it's s. So this is kind of like, if you modify this definition a little bit. So, yes?
Would an extra board help? You can draw an extra board in here.
Maybe.
Okay. And second, do you have an attribution? And you sort of say that this is due to.
I think this was invented like independently by several different people. I don't have an attribution for the original source of this definition.
Right. But the other thing is that Jules had already done a thesis on dialectical sort of stuff. So in 2014, I discussed it all with him. And I think my way of drawing this composition is a much better way of drawing.
Yeah. So this is, this is the bad way of writing it. And so yeah, it won't this is like, it's not like Jules invented lenses, and obviously it was kind of in the water, but as far as I understand, he did come up with this definition kind of, and then later realized, wait, this is kind of just like a lens.
Right, no, I was just saying that, since he had already done his thesis on things that had to do with
Sure, yeah. Yeah, and this is a good, like if we want to
he has this
give
blog post
yeah.
in 2018 saying.
Yes. And it's a good, like, if we want to cover kind of the dialectica categories for linear logic were predates the lenses in functional programming by probably a few decades, yes, which is kind of a previous that's kind of the prehistory of this, but I didn't want to go that far back. Yes. Okay, so this is kind of like lenses. So the reason I was about to erase was that I wanted to just kind of like say, so if you say a lens goes from like A is, well, okay, let me use from here, and you have, X and Y, and X S. Well, then this is like now. This looks like this, but otherwise it's still correct, and the formula for composition still works without modification. Yes. So with this definition, an open game is, a set sigma, a function sigma to lens x is y r. And so let me write it like this: an equilibrium predicate which is epsilon, which is a subset of sigma times the set of lenses from, like, you know, 2 singletons to xs times the set of lenses from yr to 2 singletons. So why is this true? Well, so obviously, you know, like this data is a function from x to y, and this data is a function from x times r to s. So these two things together give us this is a function from sigma to the set of functions from x to y, and this is a function from sigma to the set of functions from x times r to s. So the two first things together become a function from sigma to the set of lenses, and the equilibrium predicate, well, so it's, you know, sigma and then a lens from 2 singletons to xs. That's a function from, you know, a singleton to x, which is a point in x, and a function from something to a singleton, which is nothing. So that's just a point. That's just the same thing as a point in x, right? Like, this is isomorphically the set x, and a lens from yr to 2 singletons is a function from y to, stand over here so people can see the relevant things at the same time. It's a function from y to a singleton, that's nothing, and a function from y times a singleton to r. So this is isomorphically the set of functions from y to r. Okay, and now to compose, let's call this, I suppose we can call this, it doesn't really have a name, let's call this P. To compose sigma 1, P1, epsilon 1 from x is to y r, and sigma 2, P2, epsilon 2 from y r to I was going to say a set q, yes. Good. What do? Well, we say this is like the strategy set is going to be sigma 1 times sigma 2. So a strategy for this kind of composed agent is just, you know, you choose what player is doing and what's the other player doing. To play, you obviously just compose the lenses. So like sigma 1 comma sigma 2 maps to P1 of sigma 1 compose. Let me write it diagrammatic composition again. P2 of sigma 2. And okay, so finally, what's the equilibrium relation? Now, you know, so I have to tell you, given a lens from the points to xs and a lens from zq to the points, and a point in sigma 1 and a point in sigma 2, whether it's an equilibrium. So these are the tuples, sigma 1, sigma 2. Let me write this as x and k again, where like sigma 1, x, and the play of sigma 2 composed with k is in epsilon 1, and sigma 2, this is then x composed the plane of sigma 1, and k is an epsilon 2. Okay, so how are you supposed to think about this? The point is that the behavior, once you choose a strategy for each agent, then the way they interact with the environment becomes exactly idents. And then you have this extra data that tells you, well, given what the environment is doing to you, what are the good ways to behave? And then when we compose two of these, how do they interact with the environment? Well, you just compose the two lenses. Given a way that the environment is acting on them, well, what does it mean that player 1 is doing something smart? It means that given what player 2 is doing, player 1 is doing something smart in the environment that he's seeing. And what does it mean that player 2 is doing something smart? It means that given what player 1 is doing, he's doing something smart in the environment he's seeing. And so Jules draws these, let me put it here maybe, like diagrams. I'm not sure these are original with him, but his paper is the first place I saw them, that he calls them box diagrams. So you draw a game like this, it receives an input of type X, output type Y, input type, so it's R, output type S, and then, so this is like, G1, G2, C and Q, right. So this is this diagram obviously doesn't tell you anything about the composition other than what the types are, but this is kind of like how you're supposed to think about it, that like player 1 is processing information this way and then later receiving an R.
But, you could try to give us more intuition about the equilibrium predicate there, right? Because when you say equilibrium, at least I try to think about things that are in an equal power, right? And here we have a very strange thing, because we have.
So I think equal power, so the word equilibrium is in the sense of economics. And I think equal power is a bad way of thinking about equilibrium. It's an equilibrium in the sense that nobody wants to change what they're doing. It's an equilibrium in the sense that we're staying still, not in the sense that there's kind of two forces that are pushing. Well, so many equilibriums have that character, of course, that there's some cost that goes up and if we go in one direction and it's being balanced by a different cost that goes down. But this equilibrium really is supposed to mean kind of that we're staying still. So it's so one very like natural open game. This is called utility optimizer. This is an open game of type so I think this is like we could call U sub XY. This has type like X singleton to Y, and then the real numbers, and so the strategy set is the set of functions from X to Y. The play of some function, and you just use that function, and co-play is trivial because you're just producing a singleton, an element of a singleton, and then the equilibrium predicate is that if x k is in equilibrium if x is a maximum. If f of x is a maximum of k. Right. So the environment tells us what's happening and what's the utility function, what's the reward given various choices we can make, and we say this is optimal if given the actual state we make an optimal choice. Of course, there could be multiple optimal choices. Right. And so you can kind of take these things and and why like put them together, and you can draw the composition like this if you want. You can also draw it, this is just a picture. Put them together using these kinds of composition rules, and you get kind of a game where the equilibria are the points in strategy space where nobody can get a better reward by changing their decision. You could also call these like, you can call this like an optimum predicate, maybe that would be better, or immovable. Yeah, I think so. Yeah, again, this is the kind of a word from economics that Jules chose, and maybe the economists should have chosen a different one.
I think it just follows from game theory.
Yeah. This is what game theorists call. Yeah, right. Yeah, probably Nash came up with this word. I mean, so and you can kind of say that this. I mean, sometimes we call this composition rule Nash composition because it kind of tells you that the equilibria for composed games are the ones where like each person, given the choice the other is making, can't gain anything by changing their choice, and that's kind of the idea of the Nash equilibrium, right? Right. Okay. So this is game theory. So one of the things that is really important in game theory is like probability. So people want to think about like like games where you have some uncertainty both about like what you're gonna get if you depending on what you choose, and like what other people are gonna get depending on what they choose, and so on. So we want to include probability. Right. And so what we want to do is like replace the category of sets with the category that I'm going to write like this, the Kleisli category for probability, or you could also call this the category of Markov kernels. Doesn't really matter. The point is that the objects here are sets, but the functions are stochastic functions that produce probability distributions instead of just elements. And the problem with this is that the definition of lenses kind of breaks if it does this. So we need somehow and let me try to, I have a picture. I kind of want to try to explain what goes wrong here a little bit. So like if you have, so this is kind of how lens composition works, that you have like, sorry, let me use the same notation as before. Right, like you wire together the gets kind of forwards, and then you wire together the puts backwards, except that the puts also use the forwards parts as input. So you do it like this, and then so these bullet points are supposed to mean that I'm copying the element on this kind of wire, right? So the problem is that if I so the problem is that wait, what am I trying to say here? If I sorry, I'm freezing up a bit here.
You want the splitting to be deterministic or something?
Yeah. So well.
Yes, to be deterministic.
Yeah. So this kind of. Okay. Yeah. So this. Well. Okay. So this works if the gets are deterministic, but not in general. But I'm having a little bit of trouble putting my finger on why. I'm sorry. Okay, maybe I'm really sorry, but maybe I just need to skip, maybe I just need to like, sorry?
Some sort of lack of associativity of
Yeah, I think, so you can kind of,
normalize.
yeah, there's some problem that means that like if you compose lenses like defined like this, you get something that's not associative, and it has something to do with whether or not you kind of sample things once or twice, the random, which of course means that if it's deterministic, it doesn't matter. Okay, but I don't think I can really explain that. I'm sorry. So we need some other replacement for the notion of lens that works in this case, and somebody came up with the notion of optic, Mitchell-Riley. So optics. Sorry, this marker is kind of dying on me. So optics from.
Riley wrote it down, but any credits?
Oh, so Riley. So sorry.
Bartosz,
Riley.
Street.
Miluski.
Yeah.
Oh yeah, I think people actually. Yeah, it's one of those things where it was actually invented 50 years ago in Australia. So yeah. So but the paper to read on this is Riley's paper from, I believe, 2016, 17, something like that. All right, so definition. So now let C be any monoidal category. So the objects of, optic of C are pairs. And let me write them like, well, let me just stick with the symbols we already have, where like X and S are objects of C. And then the maps, from XS to YR are elements of the coend taken over objects in C of, so C from X to Y tensor M times C from M tensor R to S. So if C is Cartesian, maybe I'll just say if C Cartesian, I didn't say what lenses were for general Cartesian category. So if C is sets, this is lenses. By a kind of not that complicated argument, but I don't think I'm going to give it. So, okay, what the hell is this thing? So the the picture you should have in your head is that an optic is is something that looks like this. So there's a map from X, and then it produces, Y and also M, and then there's a different map that takes in M and also R and produces S. And so that's kind of, okay, that's what this says. Then what the hell is up with this coend thing? I mean, if you don't know what a coend is, the point is just that we want to quotient, like take, these for every M and quotient by an equivalence relation up to relation where if I have, if I have, say I have, X and then produces Y, let's call this F, then F produces N, and then I have some map from N to M, let's call it G, call this guy H, no, this was R, S, then, so if I have this data, then there's two ways I can turn this into an optic. I can say that, this orange box is a map from x to, I didn't draw the m, to, sorry, really should have gotten a new marker. This orange box is a map from x to y tensor m, and this other orange box is a map from m tensor r to s, and that's an uptick. Or I can say that the blue box is a map from x to y tensor n, and this blue box is a map from n tensor r to s, and that's also an up. Those two boxes also give an uptick, and like where the blue is equivalent to the orange. That's kind of, I'm not going to write down the equation because it doesn't really tell you anything. So this is kind of the point that this is kind of, so it's a kind of, feedback system, like it has the kind of communication information similar to a lens, except instead of using kind of x as the thing that you're allowed to depend on in the backwards part, we have this sometimes called a residual or like, working memory thing called m. And these form a category. It's even a monoidal category if C is symmetric. And this is kind of like the right approach to the right replacement for lenses for game theory with random stuff in it. So for C equals this category of Markov kernels. This gives the right replacement for lenses. For game theory. Right, and so I should say that it's not, you can't quite just write optics here. You have to do something a little bit more sophisticated with the like equilibrium relation here. But I'm not going to get into that. That's a little bit complicated. It's not super complicated. It doesn't really matter that much. Right. So this is kind of, and this is very general. This works for any monoidal category. So this is kind of, this is the point of optics. And like, yeah, from my point of view, the point of optics is to do probability theory in this context. Or not to do probability theory, to put probabilities into this kind of thing. Okay, so I don't have that much time left. So, okay, let me just kind of...
You started late.
Yeah, that's true. Okay, maybe I'll just get to kind of where I state the problem and don't explain our approach to the solution, and we'll see, if that's unsatisfying, we'll just have to live with it. Okay, so let me leave this in place for a little bit.
You can go for at least another 15 minutes.
Yeah, okay, let me go for 15 more minutes, and let's see where we are at that point. Okay, so right, so this is kind of one generalization of lenses, right? So completely independently, well, not completely independently, but like, not using this, some people, some of them were in this very room, came up with various kinds of things that are people call dependent lenses, or polynomials, or everything here, it has like 50 different names. So what's a dependent lens? So here the idea is that the backwards part, or let's stick with that. The backwards part is allowed to be depend on the forwards part, not just in that like the function that's going backward depends on the forwards part, but the types, the set of possible values is indexed over the forwards part. So I think, everybody who's been around David has seen this definition before, but let me just write it up to kind of emphasize the relation to the one we had before. So the objects of, and I'm not going to call this poly, even though it is poly, of D lens are pairs X, and then, a family of, okay, let me keep calling it S, Sx, for X in X. So, a set, and then a set of sets indexed by the first set. Maps X, Sx to Y, Ry are tuples. So first you have f from X to Y, and then you have for each X you have, and I'm writing it in kind of a weird way, but that sort of makes sense with the index ones. You have f from X to Y, and then you have gx from R of f of X to Sx. So yeah, so as before, you have a forwards map which just does it's just a function, and then if I'm here, so then it's like you have X, and then you have something in whatever is over f of X, like whatever the possible return values are if the Y was whatever f of X was. And then we produce one of the possible return values for X. Yes. And you compose these kind of the way we composed them before, except that we have to keep track of the indexes. So to compose, if gx compose f prime g prime of y. This is like f compose f prime, and then so now I need a function for each x. Okay, let me say that if gx goes from xs to yr and x y, and f prime gy prime goes from yr y to c q qz. Right. So in the forwards direction, I just compose like this, and in the backwards direction, I also kind of just compose. So it's like, it's like, g compose g prime at x is by definition, so it's gx, sorry, of course we compose in the other direction, so it's g prime of f of x compose gx, which, the types magically happen to add up, so this makes sense. So kind of, yeah, so this is a little bit abstract, but it's essentially doing the same thing as we did before, except that the dependency on x is now living in the index and not kind of being passed as an explicit argument to the function g. And you kind of like we're kind of like, we can't not depend on x now, because what function we even have to map into or out of depends on what x is given there. Right. Okay, so this is kind of a different generalization of lenses, and you can also build open games on these. There's no kind of like, and in this case, you can actually just use the definition as written, but write D-lens instead of lens. Well, you have to think about, if it's, then it's the point and the point over the point. That's also a useful generalization of open games. This gives kind of, we just call them dependent open games, but like open games where the possible utilities or rewards depend on the choices made. Okay, so kind of, the examples here are a little bit more abstract, but you can think of a game where the game begins with me choosing whether, either David is going to play a game where he's going to do something and get some utility, or Sophie is going to play a game and she has a completely different set of possible decisions and things that she cares about. And so kind of in the instant where David is running, the set of possible rewards that can come back is a different set from the version of the game where Sophie is playing the game. Okay, so and maybe I'll just note on a formal level, this gives the category of games coproducts, which it otherwise doesn't have in general. And this is kind of, on a formal reasons, this is very nice, and it kind of, we want to represent this kind of branching choice where, you can choose one thing or the other, and they kind of exist independently of each other as coproducts. That's the way we think about that in terms of categories. And so it's nice to actually give it that universal property. And you can do that if you use dependent lenses. And this is kind of connected to the fact that the category of lenses doesn't have all coproducts, but dependent lenses does have all coproducts. Okay, so now, we really want to use probabilities, and we really want to use dependent lenses. So how the hell do we combine those two things? And that's kind of, the hard problem of quote-unquote dependent optics, which is just, the two words meshed together. Right, and so let me say a little bit about why this is hard. So the basic problem is that if I have, if my f here is stochastic from x to y, if I get a probability distribution over y's, then I don't know what my g should do. If x is something, what should g be defined out of? And there's various kinds of clunky solutions you can try to come up with to this. Most of them don't really work. And that's kind of, there's various kinds of formal ways to think about this problem, but it all kind of boils down to this problem that if this is stochastic, if this has monadic effects in some way, there's not really any sensible codomain for this guy. Okay, so what can we do about that? Well, let me just give kind of the straightforward answer to what we want here. So a stochastic dependent lens again, these are just sets, so from x, s to y, r. Sorry. Oh yeah, sorry. Of course, they have to be dependent sets. Otherwise, there's not much point in this. Is a function. Oh, so now let me see if I can do this right. This is a function. So maybe I want to say this is an element of, so you take the product over product indexed by x, And so for each x, I want to produce, you know, a y and a yes, that's what I want to do, and a map from wait, okay, sorry, give me a second here. And this y to produce a y and a stochastic map from y to. Yeah, I probably want a sigma, so I want to produce. Okay, actually, probably what I want to do is I want to like let like r with a map to y be like let this be sigma y ry, right? So I want to produce, you know, an element, so a distribution on, you know, like you know, y ry to, actually I guess I didn't need this. A distribution, oh, what the hell am I doing here? Map from ry to sx, or sorry, there's a really neat version of this that I'm completely messing up. So I want a sigma distribution on functions from I want a sigma here, so I want a sigma y, and then I want functions from like, okay, so let me write like this, function from let me write Markov here, ry to sx, but this is not, this is coproduct in convex spaces. So that's kind of the you know, space or, you know, like P algebras. Right, so yeah, it's something like the join. So this is a bit you know, mysterious, but let me try to, so let me just explain what this means. So, you know, these stochastic maps are also, you know, Kleisli maps for this probability monad P. And so the set of maps like this has a P algebra structure, which is not in general free. So that's why I said convex spaces and not like, you know, not coproduct in like Markov kernels, because of course the coproduct in this category is just like the coproduct of free convex spaces is free. So the point is that you need to somehow use, like, you need to like use the convex structure of these to say what it means to produce, you know, an element of y and a map from a stochastic map from. So what doesn't work, like what you want to write is like, you know, for each x and x, an element, like you want to interpret this as a, you know, a y and y, and a, you know, a map from like ry to stochastic to distributions on P as x. And this is, so this is what you know, this is like you know, sorry, and you want to, sorry, this is what you want to write. I have a distribution, you know, I produce a random y and also a random map from ry to sx's. But this is kind of, there's too many p's here, like, you know, if you have an uptick like this, right? So this is in the non-dependent case. This one says, you produce a y and a random map, and then that random map can also produce some randomness. But there's a difference between producing a random map that, that doesn't do anything random, and then producing always the same random map. But that was very convoluted sentence. But those two things are supposed to be the same thing in optics, right? Like if this is like, R, and this is, if all these are like real numbers, and this one just says like, this one just says output the identity, and then output like, and this one is like normally distributed, and this one is plus. This one says like, in forward direction you don't do anything, and then in the backwards direction you add a normal variable. And there's two, like some normal error. There's two ways you can represent this in this world. One is you say, I'm always gonna produce y is always gonna be x, and I'm gonna, always produce the map that randomly adds normal error. And the other way you can represent this is by saying, well, y is always gonna be x, and I'm gonna choose each time a different map, namely the deterministic map that adds something, but the something is going to be normally distributed. So maybe a different way of saying is that like in here you have both x and x. You have both kind of randomly choosing a deterministic map, and you also have deterministically choosing a random map, and in this world these are disjoint except for the fully deterministic maps, but some of these are actually supposed to be the same optic. So yeah, so when I say this is wrong, I mean in the non-deterministic case this is not the same thing as optics, which is kind of what we want. Right, but this is right, and you can. So if you if C is closed, and now the category of the category of Markov kernels isn't closed, but you can pretend that you have the category of convex spaces, which is closed, and it embeds in there. Then you can. Let me just write down my definition. Then, so for C closed, then and this is the reason I want to write this down is this is kind of poly, but in a more general way. So let d opt C inside the enriched functor category of, if C is closed and has coproduct and has coproducts. Inside the enriched functor category, be the full coproducts and, I guess it always has tensors, this is stupid. Full subcategory spanned by the functors of the form some, say I and I, xi tensor internal hum si dash. Then d opt of convex spaces, contains a subcategory given by so you look at some I in I, and then you always, so let me write it like this. So sum x and x, and then you always take the unit and you tensor with, well, let me write it like the free convex space on Sx. And this maps between these are as over there. And so this is a kind, this is a kind of, this is kind of poly, but for like enriched categories or for closed categories. And this is supposed to tell you that that's a sensible, that's a sensible version of this. And, so the idea is that this is like a coproduct where, like indexed by x, where, of things that are like a point and Sx over the point. And so, so this is, the unit, which is, in convex spaces, this is actually just a point, right? But this is the free convex space on a point. I guess I should write P of Sx, since the free thing is also just the space of probability distributions. And that's what makes that work. Right. So, I suppose this is already confusing enough. And I'm sorry that it was a little bit of a mess. I'm happy to stand here and explain everything in response to questioning, since I think that's going to be more fruitful. Just want to mention that, so this roughly speaking, this tells you how to do dependent optics in a case where your objects kind of decompose as coproducts or disjoint unions of separate things, each of which is not dependent. And in each of those cases, you have Si over Xi, which is kind of constant or doesn't depend on the point inside Xi, but then you have different things next to each other and a different thing over each thing in the base. This is not kind of completely as general as you want it to be. For instance, when you talk about machine learning, you often want to talk about things where the forwards thing is some sort of manifold and the backwards thing is a bundle over this manifold, like the tangent bundle for parameter updates. And in that case, bundles are not generally speaking trivial. They're locally trivial in the sense that but they're not, you can't write a manifold as a sum of disjoint components where the bundle is trivial over each part. So, and we do have a quite technical solution to this, but I didn't really have any hope of getting to that because it's very, there's no way of explaining it in a useful way in this amount of time. I'm happy to talk about it if anybody wants to know about it, but it's pretty complicated. And I want to say it's so complicated that it's a serious downside that there isn't compared to the this is kind of an unnecessarily complicated definition of poly, but it's actually pretty simple, and our thing is very complicated, and that's a big kind of problem. So we're looking for a simpler one. Okay, so
let's stay. Sorry, I thought you were done, but.
I was just about to say I want to end here, and I'm happy to answer any number of questions.
Great.
Brendan.
Okay. I have 3 questions.
Okay.
Maybe I'll start with the most semi-technical one. So you have these diagrams here where you have the wire bending around to represent essentially this element of this coend.
Yes.
But while the sort of 4 side types, those wires are really objects in your category.
Yes.
This bendy thing seems to be a bit more subtle of a thing.
Well,
so what you're saying, if I understand correctly, you're saying in this case, thinking of that thing as an object actually breaks down because when you represent equivalence class.
Right. I guess. This is a good question. I think I don't really want to endorse any interpretation of these diagrams for dependent things,
right,
because I don't really know how to think about that. This was just to kind of explain the problem. So this we want, in the case where this doesn't depend on this, I want to get optics. And this was kind of, I was trying to explain why I don't get optics if I use this definition.
So is, can you make that technical? Like there's some sort of claim.
Yeah, so.
These in certain styles of categories that are, I don't know, set-like, then this diagram has a good interpretation that leads to an optic, but in...
Well, so, no, I want to say this diagram always leads to optics, right?
But this is a generalized definition of optics.
Right, so I want to say something, I mean, I want to say like, you know, the case like, you know, for all, like there's an element of, if you look at for all x in R, some y in R, you know, R to distributions on R. Right, there's an element, there's two different elements in here that are supposed to represent the same optic, namely this optic. Yeah, I mean, if I had to do the talk again, I probably wouldn't have drawn this diagram because as I was drawing it, I realized that, you know, this notation, like, you know, this is notation for optics, so obviously it makes it more difficult to explain two different things that give the same optic and not less. Yeah. So this is, yeah, this, you know, for optic, in the case where these things kind of, where we don't have dependency, we kind of know what it's supposed to be, namely optics, and you know, in that case we have this pretty nice graphical notation. It's like, but it's yeah, I think one of the problems, and people have some thoughts on this. It's not really something I have a lot of, like a good overview of what the state of the art is. But one of the things we're thinking about is kind of how to do diagrams for the dependent case, which is, you know, obviously more complicated.
Question. I can see that you're kind of going lenses, objects, kind of doing lenses over Markov
Sure.
things, and then dependent lenses. But you know, if I did not want to do Markov things, if
Yes.
I just wanted to go lenses and dependent lenses,
Yes.
can I go that way?
Well, it depends on, so you can definitely do like game theory in this world. That's
And
complete.
we'll have the same sort of equilibrium principle.
Yeah. That's all, like, that's totally possible. In fact, that's, I mean, you know, at present, that's much nicer than this. Like, it's much easier to figure out what's going on there, and you really don't have to change, like, you essentially don't have to change the definition at all, except you have to write like d-lens or like poly or whatever you want every time I wrote lens. Well, okay, you also have to, of course, change the objects, like, because they're going to be dependent, like indexed sets instead. And kind of the interpretation is now going to be something like, you know, you have a set of possible choices, and each choice also kind of tells you something about what information you're willing to receive from the future. So you know, you're not just choosing what to do, you're also choosing what kind of like rewards you're gonna, like, yeah, what type of information from the future or from the environment that you're gonna accept back. But yes, I mean, yeah, I think this might even be in the literature, and I can send you a paper if it is. Otherwise, I'm happy to explain it in more detail. But maybe not at this particular moment.
So a non-technical question. In this quest to understand dependent optics, are there specific game theoretic situations or problems that are motivating you?
So one of the things that we're thinking a lot about is actually, maybe I should have used machine learning as my kind of through-going example instead, because it comes from machine learning, which is that, so there's this thing called a generative adversarial network in machine learning, which is, so the way this kind of works is that, like, there's, you know, you want to use machine learning to create a system that can create like pictures of human faces, and you have, the input that you have is you have a whole bunch of pictures of faces, and you want, to generate some more. And so you train two like networks, neural networks. The discriminator, which learns to tell which faces are, to tell like human faces from your data set from other things, from other pictures. And the generator, which learns to generate like faces, right? And so basically, like one way to kind of think about this is, well, now I say one way to think about this, I start drawing and I run into this problem that we don't have a good notation, but like you can think of, so either the generator runs, and the generator, I guess, doesn't really have any, well, usually it has some input and it kind of has to just find some way of turning its input into a human face. So either the generator runs and it produces an element of like, the set of images. And then, well, I'm not really sure. So this is not a monoidal. This is not like monoidal product. This is supposed to be like coproduct composition, or and this you just choose like this is the training set. You choose a random image from the training set, and that gets output. And then so this is coproduct, so it makes sense to fold these together. And then the discriminator runs, and it says, yes, no. Oh, I guess, okay, so I take this and I produce, I take this coproduct, I produce, something in image, and I also produce, a Boolean that tells me whether it really was from the generator or the training set. So, and then the loss function just says, well, if the discriminator got it right, then he gets points, and if he got it wrong, he gets minus points. And if the discriminator gets it wrong, the generator gets points, and the discriminator gets minus points. So this is the kind of case where we want to say what happened in the past. There's two different cases, and they're kind of running they're not running in parallel. They're running independently of each other. They're running kind of either one or the other is happening, and that's I said this is machine learning. This, I guess, the way I described it, it's really a game theory thing. This is a game that these two kind of players are playing. But this comes from machine learning. I don't think it's theoretically interesting as a game theory problem, but this is kind of one of the types of things that we've been thinking about. And this is kind of here you also have it's important that you're getting you're not getting the same training image. You're getting a random one, and you want to as the discriminator, you want to find kind of a good coverage of a good understanding of the training set, of the whole training set. And as a generator, you want to kind of generate pictures that look like, all over the training set.
Is there a probability monad or anything involved here?
Yeah. So well, I mean, is this right now whatever you want can be, but you could think of this as a game in some kind of category of games built on stochastic dependent.
But where's the probability?
Well, this is a random. This is a random map from set to.
You can only use probability in that one spot.
Well, yes, but you kind of have to push it through, right?
So when you made a claim before that objects in Markov is the right replacement for probabilistic game, just moving on the right setting. What do you mean by right there? Does that just mean you can get a category, or does that mean?
Well, so it means that you can kind of get. Again, this is a little bit kind of complicated, but you can get the right kind of, like you can make sense of the right equilibrium notion for stochastic games. So you kind of want to say, right, so, okay, let me, part of, the thing is, you, like, if the game is, so your types, what am I doing? Your types look like this, right? And then you see, so you want to choose, what does it mean that you're choosing the right y given x? You kind of have to, your x isn't just an x, it's being generated by some, process that might also have generated some other stuff that affects the reward that you're going to get back. And so you kind of need and you can kind of see that this, the environment looks a little bit like an uptick. But this is kind of like, the point is that you need, your x isn't just a point in x, it's an observation about the, the context that, so in set, this, this kind of doesn't matter because it, by necessity must be generated independently of x. Like instead, you can always kind of, this is just, there's some, if you have, this is, these are independent, and then you can just fold this into the loss function. So x never tells you anything more about what the loss is going to be in a deterministic world. But, so I'm calling this the loss function because I think about machine learning a lot, but whatever this environment is. But in a stochastic world, it does, and that's kind of one of the things you need. I mean, I guess that's one of the things that you can get wrong if you don't use the right definition.
Okay, I'm going to stop the camera.